Thank you, everybody, for coming. And I can assume that you enjoy the conference a lot, because I do. And I really, really hope you will also enjoy this talk. So a little bit about me. I'm developer advocate from Quadrant, which is a dedicated vector search solution. I have background in ML, so before it was sexily called AI, know all of that stuff. And I'm also an organizer of a very cute small meetup about search in Munich. So if you're by any chance based in Bavaria, please stop by. I really like talking about search and people talking about search. And today we're going to talk about search, surprisingly, even textual retrieval, which is kind of funny in 2025 when we have all of these talks about AI, RAG, MCP, buzzword. But the thing is, behind all of this, it's still retrieval, and it's still, most of the times, on a specific use case, not ideal. So what do we usually have? We always have these two workhorses: keywords-based retrieval, which exists for goddamn know how many years. It's precise, it's understandable, it's lightweight, but it's very simple. And we have our bread and butter in Quadrant, semantic similarity search, which matches stuff by meaning. Okay, so we have them both, and usually we're greedy, we want all of that, so 2 in 1. What people usually do, they do hybrid search. Hybrid search, take one, take another, combine, fuse, use some ranking fusion, you got it. And sparse neural retrieval is another approach, which I would call more like an intersection rather than union in that case. So it's an approach where you have keywords matches, but these keywords matches are coming with a semantical understanding of these keywords in their context, so in the context of their texts. So let's debunk it a little bit before I'm gonna dig into the model which we trained and which is the topic of today's talk. Sparse neural retrieval. So firstly, let's start with sparse, how it's in general combined with keywords-based searches. So, you know, keywords in the text or just words can be represented as the sparse vector, where all the 0 dimensions refer to the vocabulary that we are using, for example, all the English words out there, and the non-0 dimensions refer to the keywords in the text we're trying to encode into this sparse representation. Okay, so what makes it possible to do a sparse retrieval on these sparse representations? We need to encode somehow the word's importance in these texts, so our query matches our document in the retrieval. And this word's importance can be encoded in different weights, in some numbers. For example, everybody knows BM25, which, based on the statistical values in the corpora, encodes some weights into our sparse representation, which allows for the keywords-based retrieval. Exists for 30 years. And the idea of sparse neural retrieval is to add some meaning, to add some machine learning into it. Because machine learning models, for example, dense encoders, they're capable of understanding the word meaning in the context, they're capable of understanding relevance. So maybe if we, instead of putting this weights of the keyword terms in sparse representations through statistics, like BM25 does, we could do it exactly with a machine learning model. Sounds kind of interesting, right? Because maybe we could go much better, at the same time stay on the precise size of keywords-based matching. So I kind of wade into the rabbit hole of studying modern sparse neural retrieval, and I kind of derived this general architecture of how a modern sparse neural retrieval looks like and how it's trained. So you take a data set, which is based on retrieval, so on the query document pairs, for example, MS Marco, everybody probably knows MS Marco in the search world. You take this query, you take a document, you put them through a dense encoder to give this high-dimensional token representation which encodes the meaning of the keywords in the context. Because dense encoders, before producing one vector for a text, in the previous layer, they have this token high-dimensional, high-resolution embeddings of each parts in this text, so each token. So usually sparse neural retrievals take them, And they put a trainable layer on top, and they basically condense this high-dimensional representation into one number. So one weight. One keyword, one weight. BM25 does it by statistics. Machine learning models do it by condensing the dense encoded representations into one number. Then you calculate the similarity score, and then you train your model to produce similarity score based on the relevance objective you have from your MS Marco. If the pairs are relevant, similarity score should be high. If they're irrelevant, low. Okay, sounds kind of super interesting. Why wouldn't we try that? Why we're not using it in our pipelines? Well, because typical sparse neural retrieval just doesn't work. And what do I mean by just doesn't work? The thing is that when you train something on your data, benchmarks on your data are perfect. Everything looks smooth, everything works. And then some other people try to test your model on other data sets out of domain. And then suddenly, on these benchmarks, all of these sparse neural retrievals, super smart and super understanding by meaning, perform worse than BM25. And BM25 exists there for hell knows what, like how many years, and it's super basic. So we tried to beat BM25, and it just didn't work. Okay, then what about Splade? Might somebody ask me, because they maybe tried to use sparse neural retrieval. They tried Splade, and Splade worked. The thing is that Splade actually works better than BM25. It's the only one known and used sparse neural retrieval model. The thing is, it beats BM25 only due to its inner document and query expansion mechanisms, which basically adds synonymical keywords to the queries and documents. And these mechanisms are very, very heavy. If you ever try to inference Splade, it's a nightmare. And if you take away from this extension and you just keep the initial keywords, the paper that I showed on the previous slide shows that the Splade is going to lose to BM25. So we end up with unusable sparse neural retrieval, which is either not performing on any domain besides it was trained on, so on MS Marco, or it's not sparse or not lightweight. That's pretty sad because the idea is great. So we decided, what if we'll try to make sparse neural retrieval usable? And what if the direction that we are going to take is not going to be searching broader, like all of these Splade models do, so expanding the documents with some synonyms, but we will just try to rank better than BM25, so with semantical understanding. And here we come to the idea, which I guess some of you might like, that if it works, it works. There is no reason to discard methods which work already for many, many years. So if BM25 works, let's just build on top of it. Let's just use this formula because, well, it's somehow performant out of the domain, right? And it's good at defining the importance of the words in the texts. The only problem of BM25 that when the texts are of the same length, for example, in RAG you're chunking, and the chunks are usually all similar, so statistical evaluation becomes not so representative. So BM25 won't understand for the word bat if it's about the flying one or if it's about the beating one. Okay, what if BM25 understood meaning? What if we added a meaning component to it and made it to understand what is behind the keywords? That was the general idea. The thing is how to express a meaning. If you try to condense it in one number, you might fail because words still have a lot of polarized meanings, which is more than one, and then it's very hard to distinguish by one number where are we going with that meaning. Dense encoders use thousands of dimensions to encode the meaning in the context. Okay, so maybe we should look more to the sides of dense encoders and produce very small meaning vectors. Then we could actually encode a little bit of meaning into them. And since the words don't have that many polar meanings, we could try to make them very small. But still, they are not very well fit for the classical inverted index, right? because in inverted index, you just put a number. Well, one author of one paper which caught our attention, which is called contextualized inverted lists, proposed to put meaning vectors directly into the inverted lists. And then when you do the keywords-based matching, instead of multiplying two numbers, you multiply two vectors, basically dot product. So this contextualized inverted lists idea, or COIL idea, so COIL, it's a little bit of a hint, was kind of interesting. The thing is, it's, again, not usable because, well, classical inverted index is not designed to store vectors. Let's keep vectors for vector-dedicated solutions. So we thought of a simple trick, and we thought, okay, what if we will find a way to kind of flatten this contextualized inverted lists and put these meaning vectors, small ones, into the sparse representations. The idea is very simple. Instead of taking one index for one keyword, you just put like a consecutive indices for a meaning vector. So if it's, for example, 4-dimensional, you just take 4 consecutive indexes, say 1, 2, 3, 4, and you reserve them for the keyword. Okay, then kinda we have an idea of how to add meaning to BM25. We can just take a BM25 score and scale it by this meaning vector of the consecutive indices into the sparse representation. And it would be a short talk if I would say that, okay, we took this idea, we took miniCOIL architecture, we took this architecture, we took mini vectors out of it, we thought of this trick, yada yada, look at us, we're reusing everything that is out there. The thing is that this talk is halfway through, and the main idea that made this talk is actually how we got these meaning vectors and how we trained them. So let's look at the problems of the COIL architecture, so contextualized inverted lists idea that I showed before. It looks pretty much like a typical sparse neural encoder. The only difference that they, instead of producing numbers per keyword, they produce small meaning vectors per keyword. But they have the same problems, and we decided to fix these problems. The first problem is pretty minor, is that they are using token embeddings. So they are working with tokens as keywords, and tokens are a bad idea to work with in keywords-based retrieval, just because tokenizers of dense encoders sometimes break words in a very weird manner. So quadrant would be Q, dry, and T, and you can't find much with this way of parsing words, basically. So instead, we remapped it to word stems. But that's a pretty trivial trick. What was interesting is that we wanted to get rid of a relevance objective. Because depending on a labeled data is a bad idea, because there is never going to be enough labeled data, especially good labeled data, for retrieval. And trust me, I worked in crowdsourcing, so I know about gathering data a little bit. And the thing is that also this relevance objective makes you kind of bound to the domain that you're trained on. So the moment you move to your use case you're interested in, be it legal, medical, whatever, it just stops working. So we wanted to move away completely and move away from labeled data. How to do that? So the goal was to somehow take this dense encoder representations that we get, any dense encoder of our choice, take a representation of a word and somehow reduct it, so do a dimensionality reduction to a small vector, meaning vector, which in this small miniCOIL space is going to be close spatially by meaning. So bats which are connected to the flying ones are going to be close together, say judged by cosine similarity, and the ones that are with like baseball and beating and hitting, they're going to be far away in that, far away in that space. So how to do that? How to guide this dimensionality reduction in a way that the spatial relationships are preserved? And the answer is kind of hidden in the picture, because if you look here, you will see the sentences. And we understand the meaning of the word from a sentence, from a word surrounding it. So you shall know the word by the company it keeps. That's how linguists defined it in the previous century. So maybe if the sentences already define the meaning, we can check out the spatial relationships between the sentences containing the same word and the different meanings. If we, for example, encode these sentences with very sophisticated dense encoder, which certainly knows how to compare the relationships. And we were like, okay, let's see if it's gonna actually work out. And we tested this hypothesis. We took like 4,000 sentences containing the word bat and embedded them with XBY embedding, which is 1,024 dimensions or so, so it's pretty sophisticated. And we projected them and checked out the clusters. Firstly, it seemed like it works because all of the sentences containing the word bat and the similar meaning, so mouse, were grouped together. All the ones that were related to baseball were grouped together. There was also some about Batman and British American tobacco. That was just weird. And the second one, it looked like bats. So my CTO was the happiest man that day, I swear to God. So okay, the hypothesis works, and we can use spatial relationships between sentences. Then our training objective can be turned to a non-supervised one, or semi-supervised one, and we can use triplet loss. So basically, you can have triplets of sentences, which are defined in the space this way. You have an anchor, you have a positive example, which is close by the judgment of the smart encoder, and you can have a bad example, so not similar example, a negative example, which is far away. And since we know the spatial relationships, due to the sentences, we can guide our dimensionality reduction. So the architecture looked kind of like this. You sample a triplet from a big pool of sentences with the same word. You take the ones that are close, that's going to be anchor in a positive example. You take the ones that is far, that's going to be a negative example. Then you take your high dimensional representation of this word bat done with a dense encoder of your choice that you want to use as a backbone of your sparse neural retriever. For example, it could be BERT or GINA or anything else. You take this embedding, you train miniCOIL on top of it, you shrink it to a small meaning vector, and this meaning vector is guided, this spatial position in a small vector space is guided by the triplet loss. And where did we decide to take all of these sentences? Instead of using them as miniCOIL, like everybody does, since we didn't need any labeled data, we could afford to use as much as we could, so the whole internet, so we decided to take 40 million of sentences from OpenWebTest, and we used Quadrant for sampling triplets, because it's pretty handy to have your own vector search solution to use it for a vector search when you want to train something for machine learning. Okay, so what is the architecture of the model itself? So the one that does dimensionality reduction. Since firstly we were working with this bat, we thought, okay, let's just be simple. Bat doesn't have too much meanings. It's a simple word. So we don't need to invent anything like super sophisticated. To be honest, as a person who studied machine learning for 7 years, I can certainly tell you the more complicated it is, the less chance that it's going to work. So only simple solutions work. So we thought, okay, one layer is enough. We're just going to train one dimensionality reducting layer with an activation function which makes sense, considering that we compare vectors by cosine similarity. And that's probably going to be enough for one word. And then we tested this one word, it worked. We were like, hell yeah, let's just scale it. Let's just train a mini model per each word we are interested in. Why does it make sense? Well, because firstly, to train one word, we needed just a CPU. Secondly, because then we could select the words that we are interested in to describe their meaning. And thirdly, it was just easy to scale to check if something goes wrong with training some specific word. And then you can just stack all of these models together. So that's how we got our first attempt to train something out of this approach, which is called miniCOIL version 1. And we released it on Hugging Face, because this talk is about something usable, so we want it to be used. It's released on Hugging Face together with an article where I give a little bit of less, crumbled description of what's happening. There are links to open source repo with the code of how to train the model, also open source links to the benchmarks that we made, because everything should be open source when you're making claims like this from stage. And as a backbone of this, we used Gina embeddings. I know that Gina guys are presenting at this conference. Shout out to Gina guys. We like your embeddings. They're super cool. And the output dimensions of this miniCOIL model are 4. Why 4? Because 42. Because I don't know. We just decided that it's a good enough number to store enough word meanings. Maybe 8 is better. It was a first attempt. We trained a vocabulary of 30,000 most used words because we thought it makes sense. And per word, we used around 8K sentences to train. Okay, so we benchmarked it. It wasn't flabbergasting, but the only one thing that we saw out of that is that it, compared to the traditional typical sparse neural retrieval, it ranks better than BM25 on unseen data. So we kind of broke the curse. Perfect. But it's not interesting to look at the benchmarks. It's interesting to look at something that works on your data. So we have a small demo where you can put your own sentences with different words and check out how are they going to group together in a miniCOIL mini space, and if they're going to be somehow properly put in the space based on their meaning. And we have 3 pre-selected examples. The demo is ugly, but I'm sorry, it's front-end engineers were very, very busy, okay? And then, so I really, really want to emphasize that this talk is about to make something usable and useful. So the first thing that I want to say is when to use it and when not to. So miniCOIL was created to be used when you want something like BM25, but at the same time, that can rank based on the semantic understanding. Imagine if you had a BM25 retriever and then a semantic re-ranker, which could re-rank all of your database that BM25 retrieved. That is kind of miniCOIL. So for example, if you're searching for titles of papers and you're searching for vectors in medicine, so miniCOIL will rank higher vector control strategies in public health, and it will rank lower advanced vector calculus for engineers, whereas BM25 will consider them similar, because by statistical means it's indistinguishable. And when you need something which needs to match, but not on exact keywords, you should use dense encoders. And if you want both, because you certainly want both, this is one of the last keywords, I swear, well, keywords, QR codes. I'm sorry, I am very QR code heavy, so I'm sorry for people trying to use phones all the time. But this is the code example, like a Jupyter notebook, where I used miniCOIL for hybrid search, exactly on these titles and the examples that I showed before in the presentation. So you can directly check it out, what's the sense and why it wins over the BM25, and maybe plug in your examples, play around, I don't know, just use it. And most certainly also maybe improve it. Takeaways. So what are the takeaways? The takeaways, that's why this talk was called so snobby, like, done right, hybrid search. In the end, I recommended hybrid search. That is the trick of marketing, right? I say that hybrid search is bad, and then I say, but use it. No, but the thing is, it's actually done right, kinda, because we did something simple, but it works. Firstly, we built on top of a reliable BM25. In worst case, if miniCOIL doesn't know a word, it's just going to fall back to it. So we're not going to work worse than BM25. Then it's very easy to train, and it's very easy to extend. If you need specific keywords, specific words for your own use case, you work in legal, you work in medical, you can just train specifically what you need, that pool. And it's pretty lightweight to train, it's 1 CPU per word. It fits the classical inverted index, so it can be reused. And it also makes sense in a hybrid search scenario, because since we are using a dense encoder as an input anyway, and we are using it for inference in hybrid search anyway, we can just kind of reuse it and put miniCOIL one-layer models on top, which adds basically nothing to the inference. So in the end, you kill 2 birds with 1 stone. But of course, it can be made better. So that's why we would be super happy if you have any ideas of how to progress more onto the sparse neural retrieval road, making it usable. So please try to use it. And also please contact me if you have any ideas or you want to speak at my meetup in Munich. I'm using this to market myself. So, and just please, I really, really like discussing all of this machine learning stuff. So I hope I look approachable. So if you have any questions, if you were overwhelmed by QR codes, which I'm putting left and right, please stop me somewhere in the corridor and I will transfer to you a presentation or answer any additional questions. But I am absolutely lost in time. I really hope that, we have a lot of time to question. Okay, then now I'm super ready to answer any questions, and thank you very much for attending this talk.
Thanks a lot for your talk, Jenny. Very informative.
I breathed in the first time in 30 minutes.
Oh, yeah, you really ran through. We have like 15 minutes left.
Oh my goodness.
Yeah.
Okay.
And do you have 3 questions? There's one.
Hello, very simple question. Have you tried using more than 4 4-dimensional vectors, like low or high, anything like that? Any studies of that sort?
Could you please repeat?
I think like in the end, your representations are like 4 by 1, like size 4. Have
Absolutely.
you tried like size 8, 16, like 2?
No, we didn't. We really hope you will. No, I mean, I am pretty sure. No, actually, I think we trained. I think I'm lying because I think we trained 8-dimensional ones. They were performing better, but we kind of decided to go with 4 because it was just like the decision, let's start somewhere and check out how it looks. I think it's based on your resources. Like if you're ready to make the vectors 8 times less sparse, but like a little bit more on precision side, train for like 8.
I actually have one more question from the online questionnaire. Super interesting talk. Have you done any experiments on multilingual scenarios?
Not yet, but I think it's pretty much feasible. That's also the plus of, I would say, being able to perform out of domain, because firstly, you can get the data, and secondly, also BM25 is not problematic to work with multilingual data. You just select the right stemmer, so the right tokenizer. So I think if it works, if people start using it, then we will try multilingual scenario. German, for example, would be nice.
I agree. One more question for you from the online forum. In terms of implementation, how did you integrate the database?
Oh, well, it's pretty nice when you work in a vector database because then you can experiment with it, kinda. So firstly, we used it for the machine learning part as an MLOps because we could store all 40 million embedded sentences and use, we have this thing which is called distance matrix API, which allows us to basically provide, like, select some number of some samples and provide a distance matrices of these vectors between them with the similarities between them. We use that for triplet sampling, and we also used a full text index to filter these sentences by the words in them, because we needed sentences for a specific word, for example, word bat. And then, well, miniCOIL itself can be integrated basically in any database. That was the reason to make it kind of reusable. So we integrated the database for the training part, but the outcome idea is reusable. So it doesn't have to be, well, it's, I would say like this. It's trained with the quadrant specifics in mind, so it's easier to adopt miniCOIL to be used in quadrant, and all the examples are in quadrant. But if you would want to, you could use it somewhere else.
All right, thanks a lot. I don't have any more online questions, but I have live questions.
Thank you very much for the talk, very interesting. I have a curiosity about latency. Have you checked a little bit, like, for example, in the comparison with BM25 scoring?
Oh, basically no difference because it's one layer. So, I mean, the thing is, it depends if we measure the dense inference part. Since we were kind of thinking of hybrid search scenario where you do dense encoder inference anyway, we kind of considered that it's already done. So, for example, if you're using like, as we use GINA, so you already inferenced the GINA embeddings, we don't count it, and we just apply the miniCOIL. But since miniCOIL is one layer, it basically doesn't add latency. It's a very small model. So it's just doing the BM25 calculations plus one layer inference.
Thank you.
Oh, wow. Now we have a lot of questions.
Hey, thanks for the presentation. I have one small question. Have you tried using the miniCOIL word model to compute miniCOIL vectors for multiple words at once? Like reuse the same model for maybe 2 or 3 words?
No, because we specifically trained the, I mean, you think for optimization or for which case? Because the idea was to just make it flexible enough that you choose a word that you want, you train a very small model, you're sure that there are enough weights in one layer for one word. But the moment when we start grouping them, like putting like 3 words into one model, it kind of starts getting less explainable at the metrics, and I don't see like a super clear benefit of optimization in that case. So no.
Oh, all right, thank you.
There was one more question here. Oh, it's gone. Okay, let's go to you.
Hi, thanks for the presentation. It was really interesting. So you mentioned you have one index per each embedding dimension. Did I get you right? And my question is, how do you at the end compute the final score? Do you take a maximum? Do you average them? Or am I completely wrong here?
Let me find the picture so it would be better explainability-wise. So we use it like this, so you get the final. Okay, I will wave my hands. I know that there is like a pointer, but I like waving hands, okay? So there is a final sparse representation we get with the meaning vectors, which is just a normal sparse vector. It's just, instead of like one index, you use 4 consecutive cells. So you use the classical dot product between them. So you just match your cell with like an inverted index with a value in it. It's going to be one number. The thing is that this one number describes 1/4 of a word, basically. But at the same time, when you do the similarity scoring, it's going to be identical to the classical keywords-based matching. Just for one word, you will look up 4 indices and do the 4 classical multiplications of 2 numbers. If you want, we can take a piece of paper after, and we will literally debunk that one.
All right, thank you. Do we have any more questions in the audience? No? All right. And no questions online anymore. So thanks a lot for your talk. And I think, yeah, you have people want to grab a coffee and question you more.
Oh, I would be super glad, guys. And I don't know, I converged from talking about this 1 hour to 25 minutes, apparently. I should have stopped like somewhere in the middle, but I am at least glad that I didn't keep you waiting. So let's compensate for me under talking this 15 minutes on the lunch break. I really, really like connecting to the search experts, and I could use some information how we can improve.
Thank you.